All right. So last week we finished up talking about reaction coordinate diagrams, and I gave you this situation where we were in this intermediate situation where we've got this star, right? And we had two options. We could go to the left path or the right path. And if we look at each of these, they have two different activation energies, meaning two different size hills they would have to climb. If we look at going to the right-hand side, you have a really large hill to climb. If you go to the left-hand side, you have a small hill. And we said if you wanted to favor the formation of product 2, all you would have to do is crank up the heat and trap your product in that thermodynamic well. This product down here is often called the thermodynamic product, which means it's just simply the most stable potential product you can get out of a reaction. If we wanted to favor the formation of product 1, on the other hand, we said down here, only run the reaction at lower temperatures. Your intermediate will only have enough energy to get over EA1, so that lower hill. It doesn't have enough energy to get over that really large hill. I do have a couple of videos on here that you're welcome to watch at home. I know some people are really big 3D learners, or sorry, visual learners, but this kind of shows on a speaker this really cool statistical distribution of little beads represented as starting materials and where they land depending on the vibration frequency of that speaker. So it's kind of an interesting situation. But there were two terms I really want you to know from this. First one is thermodynamic product. Your thermodynamic product is always going to be your potential product that is most stable. Your most stable potential product. Meaning it's going to be the lowest in energy, right? So it's going to essentially get trapped there. It doesn't have enough energy to get outside of that well once it's stuck in that really stable state. The other one is your kinetic product. And this is your product that has the lowest activation energy. All right, so if we apply a lot of heat, we tend to favor our thermodynamic product, and if we regulate the heat, we can often trap our kinetic product. The tricky thing, though, is sometimes your kinetic product is also your thermodynamic product. It really depends on the situation for that reaction, and we'll see examples of this next term in particular when we cover conjugate addition chemistry. But I did want to introduce both of these because they get thrown around a lot in chemistry. Yeah?
Can you define exactly what you mean by the most stable, like stable?
Yeah, so what I mean by most stable is you see how product 2 is lower in energy?
So you're talking about the energy, the internal energy.
Exactly. So the Gibbs free energy for that specific product is lower or more stable than any other potential products. Okay. Yeah, good question though. All right. So now what we want to do is we want to look at more complicated reaction systems, specifically reaction systems that involve more than one step. So I'm going to keep this pretty conceptual. Let's imagine we have starting material A going to B, which is our intermediate, going to C, which is our final product. So this is a two-step reaction, meaning two arrows. All right, you can show this using one big reaction coordinate diagram with Gibbs free energy, and we'll write reaction progress down here. All right, so maybe our starting materials A are down here, and we're going to some higher energy intermediate B. This is going to have some sort of activation energy to get over before it can go to B. So that activation energy is going to be likely higher than where B is. So this would be called EA1 for the first energetic barrier you have to overcome. So we'll just label this EA1 for that first hump. All right? So now that we've got B, we want to refer to this as our intermediate. And then we also want to define what the top of the hill is, and we often define that using a double dagger. So this is referred to as transition state. Does anybody know how to define a transition state, just abstractly? What's going on when you're at the top of that hill? Bonds are breaking and or being made, right? Depending on the situation. So it's the point at which your bonds are being either ripped apart or being formed. Do you think you can isolate a transition state and bottle it up? No, absolutely not. Can you isolate an intermediate? Yeah, sometimes you can actually trap an intermediate. You could bottle it up. You could look at it using IR or some other spectroscopy technique and investigate what it is, okay? So we can isolate intermediates. We can't isolate a state in which bonds are being made or broken. All right. After this step, though, we're going to go to some product C. Let me actually slide this over. I'll rewrite it, don't worry. Okay, so C is down here. We still have some sort of energetic hump to get over. So I'll call this EA2. And again, this also has a transition state, so I'll label this transition state number 2.
Capital E lowercase a sub 2, or is that capital E sub a sub 2?
Yeah, it's capital E sub a sub 2. I'm not super picky about it, though, as long as you know that they're different activation energies that are different magnitudes, right? So we can go from A to B to C, and like we said, B is our intermediate. All right, so now the question is, when we're looking at this reaction, what's the rate limiting step? Is it A going to B or B going to C? A going to B, right? So when we're going from A to B, we have the bigger hill to climb. That immediately means that EA1 is going to be our rate limiting step. So in this example, EA1 is our rate limiting step. Whoop. Which means ultimately that's the step that we're looking for when we're looking at the overall reaction rate, right? Going from B to C is so minor, it just doesn't really impact the overall reaction rate anymore. All right, so some of these get pretty complicated. Chemists, especially organic chemists and physical organic chemists, love studying these because we want to know how reactions proceed, how the bonds are made or broken. And so if you're able to isolate something like a if you're able to isolate something like an intermediate, that can prove that it's a multi-step reaction versus a one-step reaction. It tells you a lot about the overall reaction. All right, there's one other technical term I did want to discuss. This is called the Hammond postulate. It's a super simple concept that sounds fancy and scary. And that's a postulate that states a transition state, which I'll abbreviate TS, will more closely resemble the starting material, intermediate, or product, whoops, that is closest in energy. All right, so I'll show you an example of the Hammond postulate in action. Let's take this reaction that we'll actually learn about next chapter, where we've got a starting material. What would the starting material be called? We could call it a reactant, but the IUPAC name for it. Be 2-iodo-2-methyl propane, right? So we do need to remember IUPAC rules. So in this reaction, It's actually a two-step reaction. The first step is the iodine just simply falls off. Basically says, I'm out of here. When that happens, you end up with a carbon that has a positive charge. This is called a carbocation. Iodine, because it gained electrons from that covalent bond, is now negative. And then what can happen next is some other nucleophile can attack that carbocation. But let's take a look at this first intermediate step with this carbocation and draw the reaction coordinate diagram. We're going to basically ignore the subsequent step with the carbocation. So we've got Gibbs free energy over here. We've got the reaction down here. All right, what do you think is going to be higher in energy, the starting material or the carbocation? The cation is going to be a lot less stable, right? It's got a positive charge. So I'm going to put that up here. I'm going to put the starting material down here. And I'll even draw out the starting material and our products for good measure. I guess I should call these intermediates because these are pretty reactive. All right, when we do this, we've got some sort of energetic barrier to overcome. So we'll call this our activation energy for this reaction. We've got a transition state up here. Let's try to draw what this transition state looks like, right? So in this transition state, are we making or breaking a bond? Breaking. So often that's showed with a dash, meaning that that bond's kind of halfway between made and broken. And we also want to show partial charges, right? So partial charges are important. This iodine isn't formal negative yet. It's just a partial negative. And the carbon is going to be partial positive. And to show that this is a transition state, we put it into brackets. And then on the outside of the brackets, we include a double dagger to indicate that this is a transition state for that reaction. All right. So this transition state, do you think it more closely resembles the starting materials or the products based on the Hammond postulate? The products, right? So it more closely resembles the carbocation because that's simply closer in energy. It was a pretty simple postulate, but it's very important whenever you're thinking about what transition states look like and what intermediates look like and how they compare to one another. So in this case, the transition state more closely resembles the carbocation. All right, does that make sense? I remember learning this as an undergrad. I'm like, why are they showing this to me? Isn't this just common sense? Yeah, it is kind of common sense, but it's important common sense to remember. All right, so that's the last part of the reaction coordinate diagram, kinetics, thermodynamic stuff for this chapter. The remaining part, we're going to start looking into reaction arrow pushing, which we're kind of showing a little bit here. Yep.
When we draw these, do you want us also to show the transition in that efficiency?
Yeah, so the question was, when I ask you to draw a reaction coordinate diagram, do I want you to draw the transition state? I'll specify on an exam or on a quiz what I want you to show. So I'll try to be abundantly clear. Yeah. Yep.
So if we can't really do anything with the transition state, we can't isolate it or model it or whatever, why do we really care what it resembles?
That's a good question. So we've got to think about the overall energetics of the system, right? And oftentimes you have very, very complicated reaction pathways with multiple paths you can take. And so it's more just elucidating the overall reaction mechanism. That's really about it. Yeah, good question though. All right, so let's jump into electron arrow pushing or reaction arrow pushing. And this we've already seen before with acid-base chemistry. So let's go back and review. In acid-base chemistry, we had an acid that we usually represented as AH, so it had a proton coming off of it. And then we had B with some sort of lone pair. And I saw a lot of people, especially on their acid-base quiz, say, all right, the base wants that proton, so I'll show it like that. Is that correct? No. We don't show movement of protons with arrows. We only show movement of electrons with arrows. So the correct arrow notation would be to have the lone pair on your base basically reach out, grab that proton on the acid, And then both electrons in this covalent bond get dumped on to A. So our conjugate base, in this case, now has a new lone pair, a formal negative charge. Our base, the lone pair is now the covalent bond to that proton, and the base has a positive charge, or I should say conjugate acid. All right? And if we think about AH, normally these are bonds with a pretty strong dipole too, right? In this case, the reason the base is able to grab that proton is because it has a large amount of partial positive character. So if we were to draw these dipole arrows, we could show this as partial positive, and we could show that as partial negative. All right, we've got a few new terms though. One is electrophile. An electrophile is something that wants electrons, and it has a delta positive, which is why it wants electrons, or an empty p orbital. So we saw an example in class with Lewis acids and bases where bases also dump their lone pairs into an empty p orbital. In either case, though, the base was giving its electrons to the acid, right? So the acid was the electron acceptor. All right, so electrophiles are basically anything that are electron deficient or have an empty p orbital. Nucleophiles are a little bit different. Nucleophiles would be something like a base where it wants to donate electron density to a partial positive, I should say partial positive, full positive, or p orbital. And I should also clarify here that an electrophile can either be a partial positive or a full positive. So really, a nucleophile is just going to donate its electron density to the electrophile. This can happen through lone pairs, or pi bonds can be donated. They're both really good sources of electron density from your nucleophile. However, in acid-base reactions, we're normally not donating pi bonds, we're donating lone pairs, right? So that is an important distinction. Does that make sense? We're going to be using these terms a lot. They're easy to flip-flop. I always remember it in terms of electrophile, wanting electrons. So philia means to love. If you have electrophilia, that means you love electrons, right? So it's important to remember some of those Latin roots. All right? And the other thing that's really important to remember is arrow pushing notation. All right? We already saw one of them where we said you can have an arrow from your electron source that goes to your electron destination. However, sometimes, especially with newer students, you see them have an arrow that's single-headed like that. These are actually two very different reaction arrows. All right, the first one, the double-headed arrow, indicates movement of two electrons. That's what we see most of in organic chemistry, is moving a pair of electrons, not individual electrons. Yep?
In the highly unlikely scenario that you were able to rip everything off its trichromatic acid, how would you show that?
Off of a polyprotic acid?
Yeah.
Yeah, you could show that. They're each, so the question was, what about polyprotic acids? You would have to show them as each individual steps. It doesn't happen all at once.
Okay.
So it would be a multi-step reaction. And each subsequent proton you're ripping off actually has a different pKa value, meaning kind of changing the overall system for every additional proton you rip off. Yeah, good question. All right, the bottom one, though, with the single-headed arrow is movement of one electron. And really, we're only going to use these arrows when we're creating radicals or doing radical chemistry. That's something we won't see much of until second term organic chemistry. All right, so really be careful when you're drawing your reaction arrows to be careful to use double-headed arrows until we get into radical chemistry. All right, another way of thinking about it is your nucleophile is normally the source of your arrow, and your electrophile is the destination. So this is electron destination and electron source. Whoa, there's a party going on up there. All right, so let's take a look at some of the common types of nucleophiles and electrophiles. All right, so let's do nucleophiles over here. Oftentimes I just abbreviate these NU, and then we'll do electrophiles over here, which often I abbreviate as E plus or E partial plus, depending on the situation. All right, nucleophiles, like I said, are things that are electron rich. Electrophiles are things that are electron poor. One classic example of a really good nucleophile would be something like a carb anion. So a carbon with a negative charge. And the magnesium bromide is going to be the countercation. That carbon is not happy with the negative charge, right? Carbon's not a very electronegative atom. It very, very much wants to give away those electrons and form a neutral molecule. So this would be an excellent nucleophile. It's also a really good base because of that. Oftentimes, really good nucleophiles are really good bases. All right, let's take a look at another one. If we go down, we can also think of water. Whoops. Water is a halfway decent nucleophile. Why is that? Yeah, oxygen's very electronegative, and it has lone pairs, right? So in both of these situations, we've got lone pairs that can be donated. So if you think about hydrolysis in a biological system, right, where water is breaking apart biomolecules, that's due to the nucleophilic nature of water. It's a pretty important feature. Okay, the next one is pretty similar in the respect that it's a nucleophile, but this one doesn't have a lone pair. What do you think is going to be acting as the nucleophilic site? The pi bond, right? So those electrons in that pi bond can actually be donated as a nucleophile. We'll actually see a lot of this starting second term, so addition reactions involving pi bonds. These are all standard nucleophiles in organic chemistry. All right, let's take a look at some electrophiles. So on the left, we had the carb anion example. On the right, we could have something similar, but with the cation, right? So maybe we've got this carbocation. This is really, really electron poor. It's a full positive. That means it desperately wants electrons to form a neutral molecule. So that's one example we could look at. Another example we could look at would be this molecule. Why would this be a good electrophile?
Because bromine.
Bromine's electronegative, exactly. So if we think about this one, this full charge wants electrons. Over here, we've got a net dipole towards bromine. So this partial positive carbon also wants electrons. basically bromine stealing its electron density. All right? Yep. I'm actually going to draw hydrogens on here, and you'll see why when we cover substitution reactions. But go ahead, sorry.
So that, would the bromine be a nucleophile then?
Not exactly. We'll cover it in a lot more detail when we do substitution reactions, but think about the overall molecule. In this case, bromine wouldn't want to be a nucleophile because if it were to form a covalent bond, then that bromine would have 2 bonds. It's not going to be happy having 2 bonds, right? So in that case, it's not a very good nucleophile. Instead, that carbon would prefer to have something ram into it and knock off the bromine, if that makes any sense. So kind of like a billiards ball. Yeah.
On the last example of the nucleophiles there, where the pi bond's being donated,
Yeah.
is that more likely to just pick up things that balance out the carbons, for instance, like hydrogens, or is it more likely that the ring is going to break in, like just the majority of cases?
There's different examples with pi bonds acting as nucleophiles, and we'll cover them throughout the year. I mean, this is going to be a year-long process of talking about nucleophiles and electrophiles. Get ready. It'll be fun. All right, the last one is a little bit different, but we've seen this example before quite a few times already, where we had borane. It was one of our first pods where I asked you, why is borane such a good Lewis acid? And we said, well, it's got this p orbital sticking up and down that is unhybridized, right? And it's empty. So this empty p orbital also wants electrons. So in general, we'll classify a lot of our reagents as nucleophiles or electrophiles. Yeah?
Since pi bonds, I'm assuming the electrons that are being donated are the ones that are in the p, but the like shared p orbital.
Mm-hmm.
Would it ever like have any sort of motivation to put that pi bond into like a p orbital? That seems kind of like equally satisfying.
Yeah, so the question was, if you have a pi bond, which sort of electrophile will a pi bond prefer to go after or donate its electron density to? It really depends. Like I said, there's a million different types of organic reactions, and we'll see some examples of pi bonds acting as nucleophiles throughout the year. But pi bonds can behave in a whole variety of manners. So for example, what if your pi bond is conjugated and has resonance? What if it doesn't have resonance? What if there's an electron withdrawing group nearby? What if there's a carbonyl group next door? It really just depends. There's a million different situations. But yeah, that's a very fair question. All right, so let's take a look at a practice problem. And a lot of these organic reactions become fairly intuitive when you learn to spot the nucleophilic starting material and the electrophilic starting material. So let's take a look at this example. All right, and over here we've got a negative charge, and lithium is going to be our counter cation because you can't just have a negative charge on its own. It always has to have a partner. My first question for you is, what is the nucleophile? The bromine or the negative? Or sorry, not the bromine, the boron or the negative. All right, so the negative charge is going to be our nucleophile. Like we said, nucleophiles have electrons that they want to give to something else. All right, what's going to be our electrophile? The boron, why? Why is the boron sad? Did it not have a good childhood? It has an empty p orbital, right? So if we think about this, this is going to be our electrophile. All right, so using our mastery of reaction arrow pushing, what do you think is going to happen? It's going to basically zip up and attack itself. So we could show an arrow going from that nucleophile to that electrophile. And I'll show you a tip that I often tell organic chemistry students to do, is number your ring system if you are going to be zipping something up into a ring. And so what I mean by that is I put this as position 1, 2, 3, 4, 5. So it looks like we're going to be making something that's a 5-membered ring where boron is in one of the ring positions. So now we can go ahead and number this. Say 5, 4, 3, 2, 1. And then the boron still has 2 methyl groups coming off of it. What will the formal charge be for that boron? Clean this up. What's that? It'd be negative, or -1, and lithium would still be our countercation, just kind of hanging out. So with a lot of these reactions, you can essentially predict what your product would be as long as you're capable of identifying your nucleophilic site and your electrophilic site. All right, let's take a look at some common arrow pushing. All right, the first one is pretty easy. That's proton transfer. And we've seen this a fair amount already, so I'm just going to kind of breeze through this one. But we said that our base can essentially be thought of as a nucleophile. We can grab that proton, take the covalent bonds between the acid A and the proton being given up and dump that onto A. And then we get our conjugate base and our conjugate acid. So that one we've seen a fair amount of, but it's not the only one. Let's take a look at another one. This is called a nucleophilic attack because the nucleophile is essentially being very aggressive. And I'll show you an example of this. So what do you think is going to be our nucleophile? The thing on the left or the right? Left. So we said water has an abundance of electron density, right? It's got 2 lone pairs that can be donated. All right, where's the electrophilic molecule then? It's got to be the one on the right, but what specific atom? The carbon. Why? Yeah, if we think about it, that oxygen's tugging electron density, and each of these chlorines is tugging electron density. So that carbon is really electron deficient. It wants electron density from something else. So if we think about our reaction arrow pushing, we're going to start out from our nucleophile. We're going to have it attack that carbon. Are we done? No, if we formed a covalent bond to that carbon, we would violate the octet rule. But how can we fix that? Yeah, let's move the pi bond up to oxygen. And in fact, let's try to be careful with all of our lone pairs. So I'm going to draw in all of our lone pairs. So the starting material on the left, that carbonyl or acid halide, is known as phosgene. If you've read about World War I, it was one of the chemical weapons that was used pretty extensively on the battlefield, specifically for this reaction, right? It will react with the water in your lungs. Any mucous membrane that has water on it will react, so your eyes, your lungs, your skin even. And then the next step in this reaction is you'll actually generate hydrochloric acid, which will blister your lungs, and essentially you'll get an acid burn from the inside out. It was a pretty horrendous chemical weapon. One thing I am missing on here, though, is my formal charges. Where should those go? And the oxygen on top, that should be negative, right, because it received electrons. All right, what else? The other oxygen should be positive, right? So this would be an intermediate in the reaction of phosgene reacting with water. All right? The third one we've seen an example of, this is loss of a leaving group. And I often use abbreviations. I call leaving groups LGs. It's just easier and faster. And we saw an example of this with the 2-iodo-2-methylbutane, where we said iodine can actually just fall off on its own. And this results in a carbocation, so a carbon with a positive charge. And then iodine is now going to have all 8 electrons, and it's going to have a formal negative charge. So this is pretty common, as well as some molecules are inherently unstable and tend to fall apart. All right, next one is kind of complicated. This is called rearrangement. All right, so let's take this example. I'm going to actually steal our carbocation from up above. Or, shoot. Let me move this over, actually. I'm going to move the carbocation over here. And just to make things easier on everybody, I'm going to draw in all of our hydrogens, just so we know where they're at. And in fact, let me include the 2 hydrogens for this carbocation. All right, is that all the hydrogens? No, I'm missing one in the middle. In fact, I'm going to color code this one as blue, and you'll see why in a second. All right, if we think about the carbocation that I've shown, is it going to be considered a primary, secondary, or tertiary carbocation? Another way of thinking of that is how many other carbons is it attached to? It's primary, right? So that carbon that has a positive charge is only attached to one other carbon, so this would be a primary carbocation. These are unstable, meaning they are really, really unhappy having a positive charge on that primary position. So what happens in a rearrangement is you can essentially have a next door neighbor jump in and take that carbocation's spot. So in this reaction, what's going to happen is this blue hydrogen is actually just going to jump over into that carbocation position. So let me go ahead and fill in all the hydrogens. The blue hydrogen is now where the carbocation used to be, which means our positive charge is going to be smack dab in the center. What sort of carbocation would this be? Tertiary. The important thing to remember with the rearrangement reaction is you can only shift a next door neighbor to an adjacent carbocationic site, right? So in this case, that blue hydrogen that we moved over was right next door. We couldn't have moved, let's say, one of these. That would have been too far away. So you can only move immediate neighbors over into that site. All right, let's take a minute to pause here and talk about carbocation stability. Yeah. So that's a good question. The question was, can it move and then move again? Let's talk about carbocation stability and then see if we can answer that. All right, with carbocation stability, the trend is easy to remember. Actually, let's start with tertiary. I'm messing up your notes again. Tertiary is more stable than secondary, which is way, way more stable than primary, which is way, way more stable than a methyl carbocation. So increasingly stable. Whoa. All right, so if we think about the rearrangement that we just did and go back to John's question, he was asking, can we have another rearrangement after this? Probably not, because then we'd be actually going to a less stable carbocation, not a more stable carbocation. However, let's say you're going from a primary to secondary, and then there's an option to go from secondary to tertiary. Yeah, that can happen, and it can be oftentimes this horrendous mixture of products because of that. It's really difficult to predict how fast rearrangements will occur, so you often get a mixture of products. Yeah?
Why does being bonded to more carbon bring worse?
Yeah, that's an excellent question. So why is this stability trend the way it is? We'll actually come back and talk about that, but just for the sake of time, let's take a look at one more rearrangement reaction, and then we'll talk about that probably tomorrow after our quiz. Sorry, I don't mean to rush. All right, let's take a look. Oh, shoot, I forgot one other thing. This is called a hydride shift. Specifically, it's called a 1-2 hydride shift, meaning that it's a next door neighbor, so carbon 1 to carbon 2. So that hydrogen and both electrons moved over to the next door neighbor, so it's called a hydride, not a proton shift. All right, there's another type of rearrangement that we may see on occasion, and so I wanted to show you this other one. Let me zoom in a bit. Let's do example 2. All right, so in this one, we've got a carbocation right there. What sort of carbocation would this be? It'd be a secondary carbocation. All right, my question for you is, would it be wise to move one of these blue hydrogens over? No? So if I move that one over, we could try. And let's take a look at what that looks like. Oh, sorry. I'll go back and fill it in. If we do that, our positive charge would be over here. So we'd be going from a secondary to a primary carbocation. Like I said before, this is simply not going to happen. Just never going to happen. All right, so then the question is, well, are there any ways to make the secondary carbocation more stable? And the answer is yes. Instead of moving a next door hydrogen over, maybe we can move an entire alkyl group. So in this reaction, what we're going to do is we're going to take one of these methyl groups. Doesn't really matter which one, they're all the same. And we're going to dump it over to that adjacent carbon. Oh my goodness, my pens are not working right today. And when this happens, that CH3 group is now where that carbocation position used to be, and our carbocation is going to be over here. This is called a 1-2 alkyl shift. This is favorable because we're going from a secondary carbocation to a tertiary carbocation. All right, so these are the main types of reaction arrow pushing schemes we're going to see. What I gave you as an in-class activity, we obviously won't have time for. So what I'll do tonight is I'll email out the key for that, but see if you can solve it on your own and then check your work against the key. The quiz, when we have it tomorrow, we'll cover basically anything up through lecture, and then tomorrow at the end, what I'll do is come back and talk about why certain carbocations are more stable than others, and then we'll jump into new material. Yep.
If it can shift between two different, like if there's tertiary on either side of it, would it kind of like go back and forth?
Yeah, so that's a good question. If you've got multiple ways to rearrange from secondary to tertiary, you'll just get a mixture of different potential products. It's nearly impossible to control which one you'll get. And so we'll see examples of that when we get into substitution chemistry.
And then if it's honest,
Okay.